Right, hello again. Let's hopefully finish this paper in this video. So the mass of an atom of hydrogen is 1.7 times 10 to the negative 24 grams. The mass of an atom of oxygen is about 2.7 times 10 to the negative 23 grams. Using a suitable approximation, estimate how many atoms of hydrogen there are in 1,000 grams of hydrogen. So hydrogen being 1.7 times 10 to the negative 24 grams. So essentially, we compare the masses. So there's 1,000 grams of hydrogen and one atom is this much. So essentially we're asking how many of this fit into 1,000, and what that is dividing. We're essentially doing 1,000 divided by 1.7 times 10 to the negative 24. So this is a non-calculator paper, so hence why it says use an approximation. So the approximation we would use here is 1,000 divided by 2 times, we'll use these wavy lines to signal an estimate, times 10 to the negative 24. Right, so again, I don't like doing integers and standard form mixed together. It's much simpler just turn it into something you can do. So 1 times 10 to the 3 divided by 2 times 10 to the negative 24. And dividing standard form is relatively easy. So 1 divided by 2, that's 0.5 times 10 to the power of, so 10 to the power of 3 divided by 10 to the power of negative 24. So 3 minus 24, which is 27. And we need to give our answer in standard form, so this needs to be between 1 and 10. So what we do is we make this 10 times bigger. So 0.5 made 10 times bigger is 5, and we make this 10 times smaller to compensate, so 5 times 10 to the 26 atoms. A molecule of water consists of 2 atoms of hydrogen and 1 atom of oxygen. Calculate the mass of a molecule of water. So it's 2 times the hydrogen plus the oxygen. So 2 times 1.7 times 10 to the negative 24 plus 2.7 times 10 to the negative 23. So this is going to be 3.4 times 10 to the negative 24, and then plus 2.7 times 10 to the negative 23. So nice and straightforward here, really. We need the powers to be the same. So think of it as if you've got 3,000 plus 2,000, it's just 3 lots of 1,000 and 2 lots of 1,000. So if we make these the same, we can essentially just add these. That's the idea. So I generally always advocate for scaling upwards. So negative 24 is smaller, so we're going to make it 10 times bigger. So we're going to make this 10 times smaller. We're going to make this 10 times bigger. So now they have the same index and we can add them. So 2.7 plus 0.34. So that's going to be 3.04 times 10 to the negative 23. So the reason we picked the lower one is there's never any scaling required. If I scaled the other one up, we'd have to now do an index shift similar to what we did up here. So that was nice and straightforward, I hope. And that's in grams. Okay, moving on. So Diod makes cocktail glasses out of thin glass. One of their cocktail glasses is shown below. A hollow hemisphere forms part of the glass, which can hold a drink. Before each hemisphere is attached to the stem, the surface area on the outside of each hemisphere is given a decorative coating. The volume of each hemisphere is 128 pi over 3 centimeters cubed. Calculate the surface area. So the volume and surface area formulas for a sphere are given in the formula booklet at the front. So this is a hemisphere, so instead of it being 4/3 pi r cubed, it's 2/3 pi r cubed, and it's equal to 128 pi divided by 3. So times in both sides by 3, we get that 2 pi r cubed equals 128 pi, and then dividing both sides by pi, so both sides have a pi, so 2r cubed equals 128, so r cubed divided by 2 is 64, so then r is 4. So the radius of the hemisphere is 4 centimeters. So now we just find the surface area. So again, looking at the formula booklet, surface area is given by 4 pi r squared for a full sphere. So for a hemisphere, it would be 2 pi r. So the curved surface area would be 2 pi r squared. So 2 pi r squared, so pi times 4 squared times 2, so that's 16 times 2, which is 32 pi, and that's centimeters squared. So being careful here, it's a hollow hemisphere, and it only wants the outside, so we don't actually need to include this bit here. This bit is not actually part of the surface area that's glazed. Okay, so 32 pi centimeters squared. Nice and straightforward, nothing too difficult there. Okay, so Diard also makes another style of cocktail glass in 2 different sizes. These glasses are also mathematically similar. So the ratio of the volume to the smaller glass to the volume of the larger glass is 8 to 24. The height of the larger glass is 18 centimeters. So this is a scale factor question, essentially. So we need to find the linear scale factor and then apply it to the glass. So we're given the volume scale factor, which is 8 to 24. So if we were to do this, we would find out what 27 divided by 8 is. And if I'm just eyeballing it here, but it should be 3.375. So the volume scale factor is 3.375. You should not do this. There is a much better way of doing this. So volume is 3-dimensional. So to find the height, the linear scale factor, we cube root each of these. So the linear scale factor would actually be just 2 to 3. It would be cube rooting both of these. You could find the linear scale factor by cube rooting this also. So the cube root of this, so again, cube root of 3.375 would be 1.5, I believe. But my point being here that this is a bit much. If you remember earlier on, we actually did 15 cubed, I believe. Oh no, I'm thinking of something else. Don't worry, ignore me. So the ratio of the linear sides is 2 to 3. So 2 to 3, and we know the larger one is 18. So therefore, if 3 parts is 18, 1 part is 6. So 2 parts would be 12. So it's 12 centimeters. So 12 centimeters is your answer. There's the height of the smaller one. There were quite a few problems with this one. So train completed a 16,000 meter journey between 2 stations. Here is a description of the journey. The train accelerated uniformly from rest to 20 meters per second. In 40 seconds, it then remained at a constant speed for 20 meters per second for a full period of time. The train then decelerated uniformly for 80 seconds until it stopped. So you can tell they're uniform. It doesn't need to tell you they're uniform. You can tell they're uniform because all of these pieces of the graph are linear. So this is the acceleration, this is the constant speed, and this is the deceleration. So calculate the distance the train traveled in the first 40 seconds of the journey. So what it's asking for is this area here. So on a velocity time graph, so velocity on the y-axis, time on the x-axis, the area gives the distance essentially. It actually gives the displacement, but for the sake of GCSE, let's call it distance. So the distance traveled would be 1/2 40 times 20. So this is a triangle with base 40 and height 20. So that's going to be 1/2 of 20 is 10 times 40 is 400. So it's 400 meters for the first part. Calculate the total time of this 16,000 meter journey. So what it's asking for here is the total time would be the total length from here to here, essentially. So what we're going to do is we're going to break this up only slightly. But can you see that the area is actually a trapezium? And again, you are given the formula for a trapezium. So I'm going to call this section here T. And this would also be T, technically. And then this bit here, I believe we're told is 80 seconds. Yeah, it decelerates for 80 seconds, right? So now we just apply the area of a trapezium formula. So 1/2 A plus B. So A is going to be 40, 80, and T. So 120 plus T, that's A, plus B, which is T up top, times by the height, which is 20. And we're told that that's equal to 16,000. So let's see what we can resolve now then. So 1/2 of 20 is 10. So we have that 10 times by 120 plus 2t equals 16,000. So 100 divided by 10 on both sides, 120 plus 2t is equal to 1,600. So 2t is equal to 1,600, take away 120. So that's going to be 1,480. and then t is going to be equal to this divided by 2. So dividing by both sides by 2, we get 740 seconds. And we're not quite done yet because it asks for the total time of the journey. So I now know this is 740 seconds, this t. So the total time, t total, is going to be 40 plus 740 plus 80. So it's 740 plus 120, so it would be 860 seconds would be the total time of the trip. Right, can we fit any more in? Yeah, we can do this last bit by here. And then, should we do the last question as a separate video? Yeah, why not? So when the total time, oh yeah, and we just write it here, yeah, but it was, what was it, 860? Yeah. So when the train begins its next journey, it accelerates uniformly at 1.081 recurring meters per second. Write this acceleration as a mixed number in its simplest form. Okay, so let x equal 1.081. So we need to get the decimal point at the start of the recurrence window and at the end, so we can chop off the tail. So the start of it's here, so this is where the recurring starts. So we're going to get 10x, which is 10.81 recurring, and we're going to get, so 1, 2, 3, we're going to get 1000x, which is 1081.81 recurring. And now if we take the difference of these two, so 1000x take away 10x, so it's going to be 1081.81 take away 10.81. So the idea of this is that these both end in 0.81 recurring, and they'll chop the tail off perfectly. So on this side, we're going to get 990x, and it's going to equal to 1081 take away 10, so equal to 1071. So x is equal to 1071 divided by 990, and it asks for the answer as a mixed fraction. So this will go in exactly once, and then there will be 81 left over. So it will be 81 out of 990. 1 and 81 out of 990, and I noticed that both of these are in the 9 times table. So it's 1 and then 9 out of, dividing this by 9, 110. And does that go any further? No. So 1 and 9, 9/110ths would be your answer. And we'll do the last question as its own video.